So let's look at this circuit, and there's a sense of deja vu that probably occurs to you because we've seen this circuit not once before, but twice before. We first went through and analyzed this circuit using boundary conditions. We took the telegrapher equations and evaluated at the end of each line. We set up KVL and KCL, and then had a set of equations where we could solve for an unknown wave amplitudes, and from that determine the voltages and currents in terms of the plus wave amplitude. We then went through and showed how we could alternatively determine the same results if we went through and applied equivalent circuits, the accordion method, where we found the equivalent circuit looking this way, which was simply the impedance Z0, and then combined it with this series impedance, and then finally took that impedance and determined the load reflection coefficient, which allowed us to solve this side of the circuit, and then took voltage and current and propagated it to the other side, which then allowed us to determine the side on the right. And so we showed it both ways. Boundary conditions led to more equations, simultaneous equations, and unknowns. Equivalent circuit led us to a series of two equations and two unknowns. So two different ways of doing the same thing. Now we're going to try a third way, show you that there's another way of finding the answer to this particular problem. And this way we're going to use even-odd mode analysis. So if we look closely at this circuit, we really just have a two-port circuit here where we have transmission lines of equal characteristic impedance connected on either side. And if you look closely, this structure itself has a plane of bilateral symmetry, a plane of reflection symmetry. And to make this a little bit easier to deal with, we're going to take this series impedance, we're going to slice it right in half and make it into two different series impedances, two different values, and of course each one of these will have a value that is half of the original. And so clearly now we have a plane of bilateral symmetry here. This reflects over to the right and back again, and we'd have the same circuit. If you recall from previous analysis, what we did was try to determine the relationship between the waves incident on this two-port device, the waves that were propagating down toward this structure, and the waves that propagate away from the structure, which we defined as the scattered waves. More specifically, since we terminated the transmission line on the right with a matched load, we knew the wave incident on the structure from the right side, that wave, that plus going voltage, would have to be equal to 0. So the plus wave voltage coming from this side was equal to 0. In our analysis, we assumed that the plus wave voltage coming from the left side, V1, was some non-zero value. And this became our really the source of the energy in this circuit. We have a plane propagating down left to right in the direction of increasing Z. That's the plus wave voltage there, and it strikes this structure and creates two scattered waves, a minus wave propagating back in this direction and a minus wave propagating away from the structure in the other direction, in both cases in the direction of decreasing Z. And so the question is, what is the relationship between these scattered waves, V2 minus over here and V1 minus over here, in relationship to the source wave, the wave that carries the energy, the incident wave we call V1 plus. Again, V2 plus we said was 0 because of the matched load that terminates this transmission line. So if we look at our two incident waves, what we've seen is that the symmetry of the circuit, the symmetry of the structure has been destroyed. We have a wave propagating from left to right in the direction of increasing Z here, but we don't have a similar wave of equal magnitude and phase propagating from right to left. In fact, the incident wave propagating from right to left we know is 0, where this is non-zero. So the sources in this case, the wave energy bringing energy to the structure, that has destroyed the symmetry of the circuit. So to restore the symmetry in the circuit, we can use our trick that we've used before on sources that are unequal, right to left. We define an even mode and odd mode source. Now we've done this for an ideal voltage source and an ideal current source, but in this case, again, our sources are essentially these incident waves propagating toward that structure, and the result of those sources is the scattered waves going in the opposite directions. And so we can go through and define a plus wave amplitude, I call V0 plus even, and also a plus wave amplitude we call V0 plus odd. And determine the even complex wave amplitude is just what we did before. Take the sum of the two complex wave amplitudes for the two incident waves, one being non-zero, the other one being zero, and add them together and divide by 2. The odd mode complex wave amplitude then is the difference between those two wave amplitudes divided by 2. And once again, since this is 0, we get a situation where both the even mode and odd mode have the same value, which is simply the original wave amplitude divided by 2. So mathematically, we're going to say that the plus wave amplitude on the right side, the V01 plus wave amplitude, is equal to the even mode wave amplitude plus the odd mode wave amplitude. And of course, if we add those two values together, sure enough, we get back to the original complex wave amplitude V01 plus. So this is just stating a different way of stating this, again, in terms of even and odd mode complex wave amplitudes. For the wave amplitude associated with the incident wave going right to left, this V02 plus, we know that value is equal to 0, but we're going to write that 0 value as the difference between the even mode voltage and the odd mode voltage. When I say even mode, it's the even mode complex incident wave, V0 plus even, minus the V0 plus odd, the difference between those two. And if you insert them in there and take the difference, you'll get a value of 0, which of course is the correct value of the wave amplitude. So this is just sort of a fancy way of saying 0, and this is a fancy way of saying V01 plus. So, but this is how we're going to physically look at it, that we have an incident wave, which is the sum of the two even and odd wave amplitudes, and another incident wave on the other side, which is the difference between those two. So to analyze this circuit, we're going to apply superposition. Since the circuit is linear, we can go through and do this. We're going to first turn off the odd mode voltages, the odd mode sources, the odd mode wave propagating from left to right toward the structure, and the odd mode wave propagating right to left to the structure. We're going to set both of those equal to 0. So the only remaining term we have in each case for the plus wave 1 is simply the even mode wave amplitude, and likewise the same on the right, the even mode wave amplitude. So in this case, we have a situation where we have two waves that are the same propagating toward our structure. This voltage, plus wave voltage, and this plus wave voltage will have the same magnitude and same phase at precisely the same symmetric points around the plane of bilateral symmetry. This then is our even mode circuit, and because we have even symmetry, our plane of bilateral symmetry, or plane of reflection symmetry, now becomes a virtual open. And where it intersects this conductor, it becomes an open circuit, and where it intersects this conductor, it becomes an open circuit. For the other half of our superposition, then we turn off our even mode sources. In other words, we turn off our the wave, incident waves, even mode component of the incident waves propagating toward the structure, and instead we're left with simply the odd mode propagating waves. So we have an odd mode wave propagating in this direction from left to right, and then another one propagating in this direction from right to left. But remember, here we have a minus sign that's associated with this. This incident wave was the even plus odd. This incident wave was even minus odd, and so we turn off the even mode and we're left simply with the minus odd voltage there. And so if we look at any point on this transmission line, at the incident wave coming in, the voltage manifested by the incident wave coming in, and we move to the same point on the other side, the same distance from the center, so we're symmetric there, and we look at the voltage manifested by the incident wave propagating there, we'll find that those two voltages on either side will have exactly the same magnitude, but will be 180 degrees out of phase as they oscillate. So this is our odd mode circuit, and because we have an odd mode symmetry or an odd symmetry, the plane of reflection symmetry becomes a virtual short. And so now we have connected this point on this transmission line to that point on the transmission line with a conductor such that there's no voltage drop from one side to the other. So every point along this virtual short, every point, the difference between potential voltage between one point and the other is equal to 0. So let's stop and make sure we understand where we're going and what we're trying to accomplish here. We've gone through and we've written our incident waves at one non-zero and 1, 0 in terms of odd and even mode incident waves. And again, these are our sources. And what we're trying to do is figure out what is the result of those sources. If the incident waves are the cause, what is the effect? Well, the effect are the scattered waves. Actually, I have a typo here. That should be a minus, V2 minus there. The wave propagating the direction of decreasing z in either case. So we have incident waves coming toward the structure. We have scattered waves coming away from the structure, minus wave voltages. And the question is, what are these? Or at least what are these in terms of the incident wave? How do we determine that? So these are just the results like any other circuit that we might use odd-even mode analysis, where we have an odd and even mode source, and then we find the current at one spot or a voltage at another spot or whatever value there. These are the results, and we're trying to find those values. And just like in any odd mode analysis, we find that those currents and voltages can be written in terms of an odd mode and an even mode, and we find each one individually using our superpositions and then add them together to find the total result. So we're going to take the wave amplitude of the scattered wave, the minus going wave on the left side, and rewrite it in terms of a wave amplitude, one portion which is an even mode wave amplitude and the other being an odd mode wave amplitude. On the right side, that wave amplitude of the scattered wave, the minus wave over here, and I've written it correctly with a minus superscript in this case. In this case, it'll be not the sum of the even and odd mode as it was on the left side rather. It's going to be the difference between the even and odd mode result that we get, and that will be then the complex wave amplitude of the voltage manifested by the minus going wave over here. So how do we determine these values, even and odd mode values? Well, we apply an even and odd mode analysis. As with our previous even odd mode analysis examples, we see that we only need to analyze half our circuit. Once we apply our even mode sources, we turn off the odd mode incident waves and are left with the even mode incident waves. We establish a plane virtual open in the plane of bilateral symmetry, and so we can cut the circuit into two identical pieces and simply analyze one side and use the results to determine the wave amplitude, minus wave amplitudes on the other. So since this is a virtual open here and here, we have an open circuit, clearly what we have now is a lumped impedance of this value in series with an impedance whose magnitude is equal to infinity. And so the impedance of these two things in series will likewise have a magnitude of infinity. In other words, this transmission line will be terminated now in an open circuit. And we know how to deal with transmission lines that are terminated in an open circuit, particularly ones where we have identified the index, the position index at the end of the line where the load is. We've used the index z is equal to 0 to indicate that location. So our half-wave circuit simply simplifies down to something we've seen before, something really fairly trivial. We have a transmission line that's terminated in an open circuit. We know the load reflection coefficient for that has a value of 1. And so this becomes our load reflection coefficient, a value of 1 for the open circuit. Now I'll put the superscript E here to denote that this is for the even mode analysis where this is true. This resulted, remember, from the fact that we applied a virtual open because of our even mode symmetry. And so what we're looking for then is what is the minus wave, the reflected wave, the scattered wave due to this incident wave for this even mode analysis. We've done this lots of times before. We have an incident wave propagating down an open circuit with this load reflection coefficient. What is the reflected or scattered wave in this case? From our boundary condition, we know that the reflection coefficient function, evaluated in the transmission line where the load is, must be numerically equal to the load reflection coefficient. In this case, that value is 1, and so the reflection coefficient function at z is equal to 0 must be equal to 1. Notice I put again a subscript E here to denote the fact that this is for the even mode analysis. So if we evaluate the reflection coefficient at z is equal to 0, remember the reflection coefficient function is the minus wave voltage divided by the plus wave voltage, and so we're evaluating each of them at z is equal to 0. But we know that by definition the value of the minus wave voltage at z is equal to 0 is v0 minus. All right, again, that's what those wave amplitudes tell us. The v means it's the voltage, the v minus means it's the voltage, the minus wave voltage, and the v0 minus tells us it's the minus wave voltage at z is equal to 0. So this is just a notation, a shorthand notation for this value. Likewise, for v0 plus is the value of the plus wave voltage at z is equal to 0. And so putting all these pieces together, the ratio of these two things must be equal to 1. From that, we can come to the conclusion that v0 minus for the even mode is equal to v0 plus for the even mode. So a simple analysis of a transmission line terminated in an open circuit comes to this result, and we've seen this result before. This is what happens for an open circuit terminated in a transmission line if the index for the load location is equal to 0. Now we complete the odd mode analysis for our circuit. We turn off the even mode incident waves and we turn on the odd mode incident wave. So we have an odd mode incident wave here on the left side, and remember on the right side we'd have the same wave of same magnitude and phase, with the exception that the phase at every point has a shift of pi radians or 180 degrees. So we're just going to analyze the left side circuit. The plane of or the plane of reflection symmetry now becomes a virtual short, which connects this terminal to this terminal here, and so we simply have a lumped impedance that's connected directly to the bottom conductor. Take these two and combine them, we get this is our simple circuit. Once again, we have a terminated transmission line. Once again, the index is at z1 is equal to 0, so where the termination occurs. In this case, the impedance, the load impedance at the end of this transmission line is not an open circuit. It is an impedance with a value which is the series impedance divided by 2. And so again, what we want to do is from this circuit determine what is the reflected wave, the scattered wave here. Since we're doing an odd mode analysis, we get a different answer than before. And of course that is true because we have a different load than we had for the even mode analysis. What is this value in terms of this value, the plus wave, complex wave amplitude? So we need to determine what is the load reflection coefficient for this odd mode case. And for the even mode, it was an open circuit, and we knew exactly what that reflection coefficient value was, a value of 1. For this particular case, we need to go through and do a little more algebra, and we find that the load reflection coefficient for the odd mode analysis will be equal to this. So we again apply boundary conditions, and I like the reflection coefficient boundary condition. We can go through and apply the boundary condition involving impedance and solve for V0 minus in terms of V0 plus that way using voltage or current. Again, lots of different ways of getting the same answer. But I like the load reflection coefficient in this case because V gamma 0 rather is equal to the value of the minus wave voltage at 0 to the plus wave voltage at 0. In other words, it's equal to V0 minus over V0 plus, which is precisely what we are attempting to determine. So the boundary condition leads directly to the ratio that we're trying to find. What is V0 minus in terms of V0 plus? All right, what is the boundary condition? The load reflection coefficient must be equal to the reflection coefficient function when evaluated at z is equal to 0. And again, I call this gamma odd, O for odd analysis that we have in this case. And this then must be equal to this, which is equal to that. And so from this, we can determine the minus wave amplitude, V0 minus, in terms of V0 plus. The ratio is equal to this. And so this is our result. This is V0 minus in terms of V0 plus. It's simply V0 plus times this value, which of course is the load reflection coefficient for this particular circuit. All right, so what do we do now? Well, we apply superposition. For the minus wave amplitude on the left side, the V01 minus, we simply take the sum of the minus wave amplitude, even mode minus wave amplitude, and the odd mode minus wave amplitude. So we take the two results and we add them together. Shown here. For the other side, on the right side of the circuit, where we have the other wave amplitude minus wave amplitude propagating away from the structure, we take the difference between the even mode solution and the odd mode solution. So V0 even minus V0 odd minus. All right, so we take the difference, and I should have probably put a big red highlight here just to show that. Students oftentimes make this mistake. They'll add these two together here, and they'll add the same two together down here, and then miraculously these two values turn out to be the same. Well, the only way that these will be the same is if the odd mode voltage happens to be, or odd mode wave amplitudes happens to be equal to 0, and sometimes it is, but generally speaking it is not. So if you get the same answer for both your odd and even mode answers, or for both sides I should say, right side and left side, then you need to go through and make sure that you've done things properly, because like you may have likely made a mistake right here. All right, so here's one solution for V0 minus on the left side, the scattered wave on the left side of the structure. Here is the wave amplitude of the scattered wave on the right side of the structure. It's equal to this. Let's do a little algebra and see if we can simplify this. So we look at this and we notice that it's in terms of the even mode plus wave and also in terms of the odd mode plus wave. But remember, the even mode plus wave and the odd mode plus wave had the same value. It's simply the original wave amplitude, incident wave amplitude, the one non-zero wave amplitude, V01 plus, divided by 2. So we take this result and we insert it here and here, and we get this. And now we can do a little algebra and find that the V01 minus, the scattered wave on the left side, is related to the incident wave on the left side by this value. Similarly, we can determine the wave amplitude of the second scattered wave, the other scattered wave, and that would be the part of the circuit over here on the right that's ultimately terminated in a matched load. There's no incident wave, but there is a scattered wave, and that scattered wave has a magnitude, complex wave amplitude rather, that's equal to this. To determine it, we need to insert the value for the plus even mode plus wave and the odd mode plus wave, which again are the same values. We insert that here. Keep in mind this is a minus sign, where before it was a plus for the V01 minus, but now it's a minus, and so we insert the values and do algebra, and we get this result, which is a different result than we had for V01 minus. All right, so let's summarize our results. This gives us the relationship between the minus wave amplitude on the left side of the circuit, V01 minus, to the single incident wave from, again, the left side of the circuit there. Again, this tells us the first scattering solution turns out to be this value. This gives us the solution for the second scattered wave, the one that is propagating away from the structure toward the right. And again, that's the transmission line that had the matched load, had no incident wave. The reason that there is a scattered wave, though, is because the incident wave on the left, it propagates down, strikes the structure, energizes the structure, and creates a wave that propagates away on the other side. What is the wave amplitude, the complex wave amplitude of that scattered wave? Well, it depends on the incident wave on the left, but the relationship can be described with this term. If we look at these two things, hopefully you look at them and scratch your head and say, I think I've seen this before. And the reason you've seen this before, because this is the third time that we've derived these values. Once again, we started with this circuit and we applied boundary conditions and came up with multiple equations and multiple unknowns, and were able to solve for V01 minus and V02 minus in terms of V01 plus. Then we went through and tried it again, but at this time we used the accordion method, the equivalent circuit, and we crushed the circuit down into equivalent circuit, found an answer, and then pulled it back out, propagated the voltages and currents from one side of the circuit to the other, and we were able to find V02 minus in terms of V01 plus in addition to V01 minus. But in this case, we first found this, and then we found the second term. In this case, we've gone through and applied odd-even mode analysis, and I would argue this is the easiest of those three. Anytime you can apply an even mode analysis, you should, because you're going to end up analyzing two very much simpler circuits. In the case of a two-port structure that's symmetric, you end up analyzing two one-port structures. You just have two terminated transmission lines and the corresponding reflection coefficients. Students oftentimes are sort of nervous about odd-even mode analysis, and you have to think through and make sure that you get your circuits set up correctly before you do your analysis. But if you do that correctly, you'll find your analysis oftentimes, or almost always, is much, much simpler than trying either one of the other methods. Ultimately, it's up to you. What you feel comfortable with, any valid method is valid, unless, of course, I tell you on an exam or a problem to use one specific method.